Hi, good afternoon, everybody. I would be giving one aspect of blue economy, that is on the mineral and energy resources. So this session is divided into a few broad aspects. So what I will do is I will just introduce you to this area, then some of the ocean mineral resources which we have in India and how to utilize it, and about ocean energy which are available and how to utilize it before concluding. See, if you see, the Indian Prime Minister has linked the Ashoka Chakra in the national flag as the symbol of blue revolution. And we have an exclusive economic zone of about 2 million square kilometers. I'm sure that more details about this my colleague Dr. Rajan would be presenting. And we have, this is the area which you can see here marked as the exclusive economic zone, which is more because of the islands of Lakshadweep and Andamans. And because we have got resources in the international waters which actually belong to the common mankind, the International Seabed Authority, which is a body of the United Nations, has allocated for India an area of about 75,000 square kilometers in the central Indian Ocean basin. It's about 2,500 kilometers from south of India, that's from Kanyakumari, for understanding how much of resources is there and how to develop the technology for mining the resources which are available in that region. Now you know that uh, ocean is full of opportunities for food, energy, water, and there is a move to enhance our EEZ, and that would really increase the resources that is available. But there are a lot of technological challenges to harvest these resources from deep waters. This is the just a bird's eye view of the talk which I am going to give. Minerals about polymetallic nodules, placer deposits, hydrocarbons, oil, natural gas, etc. Then renewable energy and fresh water. You can see some of these pictures are shown here, about which I would just go into a bit detail within the stipulated time. If you see the minerals, starting with the beach placers, the quantity is about 632 million tons, and these are the compositions of the deep sea nodules. You can see cobalt, nickel, copper, etc. And as far as energy is concerned, you can see that non-renewable energy is concerned, we can see that this is the available resource of natural resources. Gas hydrates, this is the amount, 1894 trillion cubic meters. And energy, if you take all of them together, it's more than several terawatts. And about fish, you can see the fisheries is also included here. It's quite large. And coming to the actual resources, if you see, these are the places which are available in the coastal regions. Mostly it is in Orissa, Kerala, and Tamil Nadu. And then there are phosphorites, there also the resources are there. Then of course coming to the abyssal plains, we have got the manganese nodules. Then we also got cobalt crust, something like this, and ferromanganese sulfides are also there in the mid-oceanic ridge. And you can see this is the picture of nodules lying on the seabed, which contains copper, cobalt, nickel, and manganese. Cobalt is actually it is scrapped. It is on the surface on these rocks, and we have got underwater volcanoes where the plumes come and we get polymetallic sulfides. These are the basic resources which we would be addressing. Now, what are the challenges? I would like to say at this point in time that I'll give a comparison with ISRO. ISRO is sending satellites to the to the space, and we are sending systems out to underwater. And at one point, I would just compare and say, and you yourself decide which is more complicated, because we are having pressures of about more than 500 bar. That is 5,000 meters of water is 500 bar pressure, whereas atmosphere is vacuum and the differential pressure is only 1 bar. So that's quite easy for them. The temperatures, of course, in water, underwater, you can have nearly 4 degrees centigrade, but of course there in the atmosphere it is quite low. And one important difficulty in the underwater is that to communicate, can use only acoustic communication. That means none of the electromagnetic radiations, as you see, will penetrate into the water. It gets attenuated. Whereas in the outer space, you can communicate very easily. Only the slight time delay is there, but you can quite communicate even for the Mangalyaan or any of those things. So that is the issue. And the seawater is quite corrosive. All of you know that if if you put anything in the water, it gets corroded, provided it is very deep and it lies there permanently, which is not possible for underwater systems. So this corrosion is absent in the outer space. And more difficult is the hydrodynamics. That is, when any system is to be launched, you have to get through the air-sea interface, which is highly dynamic, and the systems get into a lot of loads and things like that, which is completely absent when it is sent to the atmosphere, because absolutely no air and no aerodynamic forces are there to act. And it is absolute darkness, more than about 100 to 500 meters. Without light and camera, you will not be able to see anything. But at least in the atmosphere, you have got one portion, you get complete sunlight, and they use solar panels to get power, and it's quite comfortable there. And we all know that we know more about the surface of the moon and the Mars than what is there underwater very close to us. So that is a very, very bad situation in our country. So we have to develop suitable technologies to get across all these challenges. Now, what is the first thing? Now, to take out manganese nodules, we require some vehicle. So if a vehicle has to move underwater, you should know what is the property of the seabed. And the property of the seabed is so unique that if you take out some material and measure its property, like for example, we call the shear strength or the bearing strength. Bearing strength is something how much load it can take. The property will change if it is taken out. So you have to measure in situ. That means the instrument should go there and measure. So we developed a in situ soil tester, which has gone up to 5,000 meters, and you can see these underwater pictures and the test data of that. So this instrument has been developed by the National Institute of Ocean Technology, and we have tested this in the deep sea. Now, in order to see that how the parameters in that particular location is, we require some sort of autonomous vehicle, and that is the remotely operable vehicle. You can see that this portion is the remotely operable vehicle. You can consider this like a satellite, and this is the tether management system, just like a satellite launch vehicle. So this whole thing is launched from the ship. You can see that it is launched from the ship, and once it reaches a certain depth, this ROV comes out of it, and it can go up to a radius of about 200 meters and measure the properties and see, and all those instruments in that will be able to utilize to measure the parameters in that particular location. So this also has been developed, and we have tested it at 5,000 meters water depth. And these are some of the pictures taken from that at various locations from the Central Indian Ocean Basin, and the basalt rock at the Rodrigues Triple Junction, the nodules collected from the CIOB, and some of the organisms which are observed at Krishna Godavari Basin in Bay of Bengal. So these are some of the test results. And we also had a test done at the Rodrigues Triple Junction. You can see the ROVs in that particular location, and the pictures which are taken from there has been transmitted from our ship Sagar Nidhi through satellite to NIOT, where at that point in time Dr. Rajan was the director of NCOR, and we were just sitting and viewing it at NIOT. The live images about 4,000 kilometers away is the first time we have done. So this is the technology that we have developed. Now coming to the actual mining, we have this type of machine which is a crawler based one, which will sit on the seabed and move and collect the manganese nodules which are on the seabed. And you can see that this is the collection mechanism which collects it here and pumps it to the surface. We have done a test up to 500 meters, and we are in the process of taking it up to 6,000 meters in the future. So this is the actual 3D model of that, which we will be working in the future for mining of nodules from 6,000 meters. And we also have in future a program to have a manned submersible wherein 3 people can be accommodated in the sphere, and it can go up to 6,000 meters water depth with an endurance of about 12 hours. So this is a new project which we will be taking up and uh, designing and manufacturing it soon. Now I will move on to the area of ocean energy. I will touch upon these aspects. Gas hydrates, which is of course a non-renewable one. It cannot be considered as a green one, but offshore wind, ocean thermal energy conversion, wave energy, ocean currents, and its offshoot as desalination in biofuel, all these things are green, and I would just touch upon quickly all of them. Now if you see, this is the Indian energy scenario. The Niti Aayog site, if you go, a good amount of work has been done by them, wherein we can just identify what is the energy portfolio in 2017 and what is the energy portfolio in 2047 based on the amount of renewables and non-renewables which you will be using at that point in time. So you can tweak it and get it into various aspects. So this you can go and have a look, but it is said that by 42% of hydrocarbons have to be imported even in 2047, even after significant use of renewables. So you see that these are the locations where we have got gas hydrates, and the gas hydrates is nothing but solid methane which is available in Krishna Godavari basin, and this is the estimated resources. You can see by bottom seismic reflectometer, it has been identified by various institutes, and we have developed something called a coring system which can sit on the seabed and drill up to about 100 meters and collect the sample for ground truth evaluation. So this is undergoing sea trials. And if you see renewable energy, about the wind aspect, my colleague Dr. Ramanamurthy would be giving a session tomorrow on this. We have a national wind energy mission which is targeting about 56 gigawatt by 2025, and these are the locations, that is in Kanyakumari and Rameshwaram. These are the two locations where we have got good wind potential, and wind resource assessment has been done, and a good plant load factor has been obtained for 3 megawatt turbine, and this is the power production you can see here at the various locations. And the commercial viability also has been proven because the IRR is more than 10%, which shows that it's highly economically viable. And the substructure designs are being done by our team, taking into account various hydrodynamic and earthquake effects, things like that. Coming to the ocean thermal energy conversion, which is the very apt technology for India, we have got a difference in temperature near the equator between the surface and the sea bottom, and this temperature is used to run an ammonia turbine. You can see that this is the cycle where the hot water is used to evaporate ammonia, and a turbine is run, and that ammonia is cooled by the deep sea cold water, and thus energy can be generated. So this is one basic aspect. Next one is on ocean current. There are various currents which are there in the waters. You are all aware of that, and water is highly dense, so we can use this to generate power. And we have done some work at Andamans, and we have used a current turbine to generate power there. Now coming to the wave energy, which is not that much useful for, or rather it cannot be utilized much for India, because we are away from we are nearer to the equator, and the waves are quite less compared to the other waters near the poles. So we have a wave energy platform which was done at Viziñam in Kerala, where the wave of movement has been converted to air movement, and air turbine was rotated to to generate power. And this has been extended, the OTEC has been extended for desalination, where we have set up some plants in the various islands of Lakshadweep, where the warm water is taken in a chamber and evacuated, and the steam so available is cooled using deep sea cold water to generate fresh water. So this has been done already, and you can see that these are the pictures of that, and we are going to set up a OTEC powered desalination plant in the Avaratti, where there is absolutely no carbon footprint. And we are also working on algal biotechnology, where Chlorella vulgaris is an algae which has got potential to get lipids, and this has been extracted, and we have run a vehicle with B10 biodiesel, that's 10% biodiesel. We have taken that and we have run this vehicle. And coming to the end, it is really a challenge to work in offshore technology, and you know that we have put lot of strides in offshore and deep sea technologies, and we really require a lot of students, lot of youngsters to work in this area. So just I would like to conclude like this, that is, you know, there is an extension of the philosophic words of wisdom that is said that if you protect truth, the truth will protect us. That is dharmo rakshati rakshitaha. So I'm just extending it and telling that if you take care of the ocean will take care of you. Thank you very much.